Okay, so today we are going to look at arc length of our parametric equations. And we've done arc length before of rectangular equations, and I know we've never called them rectangular equations before, but all the equations you've ever done have been in rectangular form. And do you remember how it was like you take 2 points on the graph, and like as you connect them, it's that length of the graph, which is cool. You're finding the length of something that's not a straight line, which is nice. I think this was unit 6 where we did this. Do you remember it was when we did the volumes of revolution and all that? It was in there with that unit. All right, so let's review that formula. It was integral from A to B, and do you remember it was like this gigantic square root? And then underneath it, it was 1 plus the derivative of x squared. And remember how I said like set it up blank, like with a blank in it, dx? All right, that is rectangular. And that's what we did back in unit 6. That's just your review of that. We're going to do the same thing with our parametric equations, and it is practically the exact same formula. So it's not really, I don't want you to view this as like new information. We're just like kind of adjusting our old information, all right? It's integral from A to B, draw yourself a gigantic square root, and it is x prime of t squared plus y prime of t squared dt. So that is your parametric version of the equation. I'm gonna let you write it and let it sink in for a second. I just want to talk about it, how it's not really a brand new equation. You just have both x and y in terms of this parameter t now. So this is really the same, but like when you have rectangular, you know how you like y in terms of x, like you have y equals in all the x's. What would be the derivative of x? 1. It's the same equation, it's just now you have x in terms of t. Does this make sense? The exact same thing. We're just going to practice a couple problems with this. That's really all that this lesson is being able to use this formula. So I have what I think I put 4 problems in here. I have 4 problems. We're going to do 2 of them completely by hand and work them the whole way out, basically so that we can just, keep our skills of being able to find antiderivatives sharp. And then I have a couple that we're just going to set up and kind of like simplify down a little bit. So this would be integral from -1 to 3. And remember what we're finding. If we were to graph this, we're finding the length of the curve from where t is -1 until t is 3. So integral -1 to 3, draw yourself a gigantic square root. And then what I would do is I would write blank squared plus blank squared dt. Just set up the skeleton of the problem, or like the framework, so to speak, and then you can just go back and fill that stuff in. It'll kind of calm you down. You'll be like, hey, I have this set up at least right. So the derivatives are what go inside of there. What is our derivative for x? I'm starting you off with an easy one, all right? 3, and then derivative of y, -2. All right, so let's see what that's going to give us. Integral from -1 to 3. What do we have under there? 3 squared would be 9, -2 squared would be 4, so 9 plus 4, 13. Looks weird because it's a square root. Pretend it was just a 13. What's the antiderivative of just 13? It'll be 13t. This one just happens to have a square root, so it would be square root of 13t such that, and then -1 to 3. What's that? Oh, did you use up like the whole sheet? Okay, well, I kind of did too. All right, so upper boundary minus lower boundary. Upper boundary plugging in 3, it would be 3 square root of 13 minus -1 square root of 13. That would be 4 square root of 13. That's like essentially it. That's the topic. That's the concept we're covering. We're just going to practice that a couple more times. And again, I just have us working this whole one out so that we can practice, basically just practice doing integration more than anything else. All right, so it's going to be integral 1 to 4. Draw yourself an enormous square root, blank squared plus blank squared underneath of it, dt at the end. All right, so what's our derivative for x? 12t, perfect. Derivative for y, 6t squared. I'm going to have us fight our way through this entire one, right? It'll be healthy for us, right? Integral 1 to 4 square root. All right, let's see what we've got. What is this first part going to give us? Good, 144t squared plus, and then this would be 36t to the 4th. Good. Those aren't like terms, so we can't put them together. Any thoughts on like where you'd want to head with this next? Like, what do you want to try? Before we can square root anything, good, let's go ahead and factor out. What can we factor out of both of those? Even bigger than 12, actually. We can take out 36, and I heard you guys say the t squared. So that'll leave you with 4t squared plus, or no, not t squared, just 4 plus t squared. There we go, dt. Now this part we can square root. So square root of 36 will be 6, square root of t squared will just be t, and then the 4 plus t squared has to stay underneath of there. Now what do you want to try? Again, I was going to let you guys struggle through this one. What would you try? Well, you have to do an antiderivative somehow. It's not going to be by parts. It won't be that complicated, but you're in the right place in your brain. What else have you got in that toolbox? There we go. U substitution. What are we going to let u equal? Good. And so du would be good. Perfect. Now, you want to compare that to what's in the problem. We have 2t here, but it's 6t in the problem. So the adjustment would be to multiply by 3. And I don't have a highlighter out. I'm just going to underline. We're going to replace the 6t dt with 3 du. So 3 goes out front, du goes at the end. What's still there? Like, what didn't I highlight? Square root of u. I'm going to write it as u to the 1/2. And then we're going to adjust the boundaries. It's not hard, but you have to do it. All you have to do is take the 1 and the 4, plug them in for t, and see what you get. So if you plug in 1, what do you get? 5, good. And if you plug in 4, 4 squared is 16, plus 4 is 20. All right, so antiderivative of u to the 1/2, you would add 1. So it would be u to what power? 3/2, good. That means out front, a 2/3. Hey, but that 3 is still there, which is actually kind of good, because what will happen? Yeah, good. Those will cancel out, such that 5 to 20, and we're going to do upper boundary minus lower boundary. So that would be 2 times 20 to the 3/2 minus 2 times 5 to the 3/2, which is a great answer. We worked hard for that answer. Again, the reason I had us go through that was less about arc length, because I mean, I could show this to you and 2 seconds later, you've got it. You know what I mean? It's a formula and you memorize it. But I thought it would be worthwhile to go through how to factor things, square root, do a u substitution. It took you guys a while to remember that, which is why it's good to review it. All right, let's just try a couple more. We're just going to set up and reduce these down. We won't actually do the entire antiderivative for these. All right, so it's going to be integral 0 to pi. Draw yourself an enormous square root. And then underneath of it, you're going to have blank squared plus blank squared. And then the derivatives are what go inside of there. Okay, this is also reviewing how to take a derivative. This is going to involve a chain rule. We're going to bring the 2 down. It'll drop to a 1. So 2 cosine of t, and then you have to chain on the derivative of cosine, which would give us what? Good. Did anyone get that on the flashcards in Quizlet? I'm sure it was on there. Cosine gives you negative sine. All right, and then this one. So what is that going to give us? Same process. Good. 5. Oh, I didn't write the 5. 5 sine to the 4th. And then times the derivative of sine, which is cosine. Perfect. I'm just going to have us square that stuff to like reduce it down. And then we'll stop there. I'm not going to have us do like this one by hand. All right. So integral 0 to pi, gigantic square root dt at the end. Let's just square that stuff. So 2 squared would be 4. It'll be cosine squared of t, sine squared of t. I'm not worrying about the negative because when you square a negative, it's going to turn positive. And then plus this one will give us what? 25, good. Sine to the 8th of t, and then cosine squared of t. That would be super fun to do an antiderivative of, huh? I'm not even actually 100% sure how you would do that. Yeah, some of them are not like able to be done by hand. You know what I mean? Like, do you remember how we did differential equations and some of them just aren't separable? Something like this would be like multiple choice, and they would be like, which one of these would give you the answer? And like, you'd pick that as your answer. All right, let's just try one more. Right, so this would be integral 1 to 7, gigantic square root, and then inside blank squared plus blank squared. So derivative of x, that would be 6t squared plus 1. And then derivative of y would just be 8t. So this one's actually going to sharpen our algebra skills more than anything else. When you do 6t squared plus 1 squared, you have 6t squared plus 1, 6t squared plus 1, and you have to distribute all of that to each other. So our integral stays, this gigantic square root stays. It would be 36t to the 4th, good. And then you'd have 6t squared plus 6t squared. So it would be 12t squared, good. And then 1 times 1 is 1. And then this one's a bunch easier. This would just be t squared, perfect. So yeah, this one was hard on the algebra. And then last thing, you can just do the like terms. So underneath of here, we'll have 36t to the 4th plus, what is that going to be? 76t squared plus 1.